opportunity of being here. It's my first time in Brazil, and it's very exciting also to be in this very prestigious center for theoretical physics. And the focus of my talk is really on the electromagnetic structure of light nuclei. And electromagnetic probes or electromagnetic observables are really useful to understand the structure of nuclei and to analyze the effect of many nucleon correlations and current, which is going to be the focus of this presentation. Specifically, I will analyze two kinematic regions. This is just a sketch of the double differential cross-section for electron scattering from nuclei, a fixed value of momentum transfer as a function of the energy released into the system. And I will discuss observable in the elastic region, so understanding the shape of nuclei, and also observables in the quasi-elastic region. That is how nuclei respond to the electron scattering from them. And comparatively, the quasi-elastic region is simpler than the low-energy region. And that is because in the quasi-elastic region, in first approximation, the nucleus can be described as a collection of uncorrelated nucleons. But as we lower the energy, we start seeing collective phenomena like collective excitation and clusterization inside the nucleus, which become really important and really affect this observable. So these are the kinematic region, the elastic and the quasi-elastic, and I will focus on the role of many nucleon correlations and currents. Schematically, these kind of electromagnetic probes are really useful to validate the nuclear model. There are a lot of data, and in most cases, they are known with great accuracy, so they really put stringent constraint on the theoretical model. But they are also becoming relevant for other experimental endeavors, for example, in fundamental symmetries and neutrino physics. And this kind of experiment needs accurate theoretical calculation in order to meaningfully interpret the data. And so these kind of studies are relevant to understand nuclear structure, but they have also other implications. As I said, the observable I will discuss today are electromagnetic form factors, so the electromagnetic shapes of nuclei, moments, decay, and electron scattering. I work within the ab initio framework, and today we will have several talks based on this paradigm, where we describe the nucleus as a collection of interacting nucleons. They are correlated in pairs and in triplets via two- and three-body interaction. There are computational methods to solve the Schrödinger equation, the many-body Schrödinger equation, and that is kind of a reminder that we work in a non-relativistic framework. Of course, we are retaining several degrees of freedom, so the position of all the nucleons, their spin and their isospin, and therefore the problem becomes computationally expensive as the number of nucleon increases. And therefore, we have to acknowledge, of course, the resources provided by high-performance computing. The ab initio framework back in 2010 was confined in the lower part of the nuclear chart. This figure is from Heiko Egert, and showed the development that occurred from 2010 to 2020. That is due for several factors: increased resources, development of new computational algorithms, and also development of new interactions that are manageable within the computational methods. Specifically, in the calculation I'll present, we use two nuclear Hamiltonian. The first utilizes the AV18 two-nuclear interaction in combination with either the Urbana-9 or the Illinois 7 three-nucleon force. And other calculations are instead based on the Norfolk models developed by Pierulli and collaborators. Both these interactions are phenomenological. They have parameters. Of course, in the case of the Norfolk model, they are called low energy constant. And they subsume underlying quantum chromodynamics or dynamics associated with degrees of freedom that have not been explicitly accounted for in the theory. These parameters are fitted to reproduce data, a large database for, in the case of two-nucleon systems, a large database of scattering data. But in general, they have a one-pion exchange mechanism to describe the long-range part of the nucleon-nucleon interaction. An intermediate range part is mediated by multiple pion exchange, and we also have short-range contribution. And for example, the AV18 and the chiral interaction differ in the way these contact short-range forces are parameterized. The AV18 uses Wood-Saxon-like wave function, whereas the chiral utilizes a Gaussian representation of the short-range part of the interaction, with strengths that are determined by comparison with the experimental data. And so just to give a sense, the Norfolk interaction have 26 low energy constant in the two-body sector. They fit about 3,000 points, and the three-body force includes 2 low energy constant. And there exist 8 models, depending on the fitting strategies and the Gaussian representation of the short-range part, as well as cutoff used to get rid of singularities. The existence of 8 models allows us to assign a model dependence or 2 the theoretical predictions. So both the AV18 plus Illinois and the Norfolk interaction have been used to calculate the spectra of light nuclei. In this figure, the experimental data are given in green, and the AV18 in blue and the Norfolk in red. The agreement is very satisfactory for light nuclei, and is a sort of validation of the microscopic picture of the nucleus. So as I said at the beginning, the main interest is to understand this many nucleon correlation, in particular two-nucleon correlation. This is a pedagogical picture that shows the interaction as function of the interparticle distance, where the long-range part is driven by the 1 pion, the intermediate by 2 pion, and then we have the repulsive core. And these interactions are responsible for many properties of nuclei. First of all, we have, for example, the rich structure of the deuteron. It's a spin-1 particle, so it can be polarized, and one can use, can study the parallel and anti-parallel configuration. And these holes, for example, are induced by the short-range repulsive core. But these kinds of two-nucleon correlation are also responsible, as we saw yesterday in the presentation by Nir Barnea, of other properties at large values of relative momentum. These are calculation of two-body momentum distribution. So this is the probability of finding a pair of nucleon with the relative momentum little q on the x-axis, and the center of mass momentum big Q that in this figure has been set to be equal to 0. And here you have the blue line represents the two-body momentum distribution for proton-proton pairs, whereas the blue line represents the momentum distribution for neutron-proton pairs. And this enhancement is induced by the tensor correlation, so the two-nucleon tensor part of the correlation. That is to say that two-nucleon physics is important at low energy, but also if you explore this kind of kinematics, which can be also probed in electron scattering experiments, such as triple coincidence experiment at Jefferson Lab. As I said at the beginning, the focus is on electromagnetic properties, and therefore we need a way to describe how the electron interact with the system. We include one-body operator, so the electron interacts with individual nucleon inside the system. And we also account for two-body correction that accounts for the fact that the two nucleons are interacting in pair. And these are found to be important to explain the data, but also informed by the theory. So this is the current conservation in momentum space. So our nuclear Hamiltonian is correlating nucleons in pairs and in triplets. And in order to balance this equation, the current should in principle include two and three body components. We include up to two body components in our calculation. And the first observable that I'll discuss is a static property of nuclei. So magnetic moments. Magnetic moments are, or magnetic properties in general, are interesting. And I'll tell you in a second why. First, let me briefly mention the kind of models we utilize for the two-body currents. If we correlate nucleons in pair using the AV18, then we exploit current conservation to construct two-body currents that satisfy current conservation with the AV18. If we utilize the Norfolk interaction, then one can exploit effective field theory to build these operators, and they emerge, for example, for the current operator in this way. And the vector part, for example, is the emergence of two nucleon current operator. The pion is being exchanged between these two nucleons, is carrying a charge, is moving charge around, and therefore the electromagnetic field can couple with this pion. And of course, you have other terms that are mimicking the intermediate and short-range part of the correlation between two nucleons. Another point I would like to make is that the ab initio method have inputs, and these inputs are anything that is related to the nucleonic property or hadronic coupling. So if they are available from experiment, we use them, we use the experimental data. That is, for example, the case of the electromagnetic form factor of the nucleons. But there are instances where they are not well constrained, and so one should in principle resort to a non-perturbative solution of QCD, such as lattice QCD calculation. Okay, so now I'm going to give you the first example. As I was saying, the magnetic properties are really interesting and really allow you to have a picture of what's going on inside the nucleus, and that is because nucleons like to pair up. And so when you study magnetic property, you are isolating the single particle contribution. And here in this figure, the experimental data are given in black. Here is the proton and the neutron magnetic moment, as well as the deuteron, this empty star. And the calculation in blue are based on the single particle picture. So you're just summing up the magnetic moments of the individual nucleon. So you have the spin magnetization of the neutron and the proton, and the convection term parallel to the orbital angular momentum of the proton. And you get the bulk properties. So odd, even nuclei line up in the upper part, and their magnetic moment is driven by the valence proton. But if you want to reach agreement, you must include these two nucleon effects. The full calculation is given in red. And really, there are, looking at these observables, you can gather information about the clusterization inside these nuclei. So you have, for example, beryllium-9 that is primarily made of two alpha particles and a single neutron, a valence neutron. Therefore, the single particle picture is sufficient to reach agreement with the experiment. In the case of carbon-9, instead, you have an alpha particle, helium-3, so essentially a neutron, and the two valence proton, and so there is a lot of exchange between these three particles, leading to a large two-body contribution. So this calculation is somewhat dated and is based on the AV18 and has been recently updated, or similar analysis have been performed based on the Norfolk interaction. Qualitatively, we found the same behavior as discussed before, and in this figure, the contribution from two-body current is emphasized by this arrow, this pink arrow. Empty symbols are without two-body current, and full symbols are with two-body currents. This work is done with Graham Chamber-Waltz, Garrett King, and Alex Nyek. And also recently appeared in the literature work that analyzed the effect of two-body currents in magnetic moment of medium mass nuclei by Miyagi-san and collaborators. And in this figure, the experimental data lines up to 0. Everything is normalized with respect to the experimental data. And the effect of two-body currents can be appreciated comparing these two symbols. Okay, so these are static properties of nuclei. We also study the shape of nuclei. They can be inferred by looking at the form factors. This is the elastic cross-section for electron scattering. You have the longitudinal and the transverse form factor, in addition to kinematic terms that are known. The magnetic form factor is essentially proportional to a matrix element of the vector current operator, whereas the longitudinal form factor is proportional to a matrix element of the charge operator. And we first studied the magnetic form factor, and here is a comparison where the experimental data are available. In this figure, our final results, comprehensive of two nucleon currents, is given by this band. So the Norfolk interaction are not built order by order, but the current operator, yes. And so this thickness represent an estimate of the truncation in the chiral expansion only of the current operator. So the agreement is satisfactory. This is the first quantum Monte Carlo calculation for this observable. We include all the multiple participating to this form factor. So here is the expression of the various multiple. And they are really important to, for example, fill in diffraction minima and reach agreement with the data. So here is a comparison with experimental data, which here is a collection of the literature we found on the topic, and is somewhat dated. The most recent analysis is from 2001. Here are some predictions, and we do understand that this could be, experimentally speaking, very challenging. These are very short-lived systems, but perhaps some of them can be accessed. And one thing that can be appreciated in this figure that is common to also the figure I showed before is the role of two-body currents in this magnetic form factor. Calculation based with the one-body current alone are in red. If you add the two-body currents, you get this black line. So they are not negligible, and they are useful. Okay, here is not visible, but they're important to reach agreement with the data. Other feature that we observed, especially by looking at mirror nuclei, so in case of carbon-9 and lithium-9, is that the M1 and M3 peak, so the blue and the green in this figure, swap in mirror nuclei, and this is a property associated with the one-body current operator. So I can give more details. But because of this reason, it would be perhaps interesting to look at beryllium-7 so that one has data for a set of mirror nuclei. Okay, the same thing is been done for the charge form factor. So these are related to global property of the system. And in addition, the two-body correction in the charge operator are kinematic in nature, so they depend on Q over M. And therefore, their significance appears only for large value of momentum transfer. So, and they are important again to improve agreement with the data. So this has been published. So this is an old slide. What is instead just being submitted is this work on charge and magnetic radii. So this work is based on analyzing the low Q behavior of the form factor. So this is just a definition of the charge radius as a low energy, low momentum behavior of the charge operator. In this case, as we saw, as I just showed you about the longitudinal form factor, there is not really model dependence at low Q. All the chiral interaction provide collapse at low value of Q. What is participating into generating this error, so these are the theoretical prediction with the error bar, is the sensitivity to the different fitting procedure to extract this radius. So those are larger than the model dependencies, which are not even quoted here. Another information in this figure is that some of the observable, primarily those given in green, are from EE prime scattering data, whereas those given in blue are from atomic spectroscopy. Another point I would like to make about this is that, of course, you can in principle extract this object by just studying the wave function and extracting it using the wave function. However, when you do so, the inclusion of size effects, for example, the radius of the nucleons, two-body effects, relativistic correction is not linear, is not trivial. When you use the form factor, everything is included. So you have the shape of the nucleon form factors, and you have all the two-body correction, but then nothing comes for free, and so you are left with this problem of extracting or making sensitivity analysis in the extraction of this object. For the magnetic case, there are, of course, very limited, in fact, two experimental data, and we utilize the same procedure. A comment here is to be made about the role of two-body currents in this object. For the magnetic moment, we found a 30-40% correction, but here is really up to 5, maximum 10%, but only because it's a square root of the matrix element. So they are, in a sense, reduced. Okay, and just to give an example of application to M1 and transition in electromagnetic observables, these are calculation of M1 and E2 based on the AV18. They show again the relevance of two-body effects also when you explore or you go away from zero energy. And perhaps another important point, especially for practitioners of computational methods for larger nuclear system, about 60 to 70% of the two-body currents, which we include up to one loop, is really driven by the one-pion exchange. So perhaps 3-level is good enough, depending on what you have to do clearly. Okay, so I think I have 5 minutes, and I'm going to just try to connect with perhaps near Barnea's talk yesterday and talk about electron scattering. So this is the double differential cross-section. It depends on the sigma mot, VL, and VT, which are all determined by the kinematics entering the scattering, so scattering angles and momentum transfer. And the nuclear responses is really how the nucleus respond to this electromagnetic probe. The longitudinal one is induced by the charge operator, the transverse is induced by the vector current operator. You need knowledge of the ground state, the transition operator, so we just discussed, and all possible final state that can be induced by this transition operator. Knowledge about all possible final state is really the main complication in this kind of calculation, but there are several ab initio methods that exploited integral properties of the response function along with the closure of the final state to create an object, which is given here, for which you just need to calculate the ground state while still accounted for all the physics. So this is the response function. This is a kernel that you utilize in combination with the closure relation, and this is the integral transform. And this object requires knowledge only of the ground state. There are two main kernels that are currently utilized. One is a Lorentz integral transform method, and here we have Sonia, Francesca Bonaiti, and as of recently also Gaute Hagen, that combine the LIT with a couple cluster to study scattering from large nuclear system as opposed to light nuclei. And so this is a longitudinal response from calcium-40. Instead, the quantum Monte Carlo group utilize a different kernel and study Euclidean responses in imaginary time, and has been applied extensively by Lovato and collaborators to study both electron and neutrino scattering. So these processes are, we learn a lot of things from these studies, particularly on the role of two-nucleon correlations and current. And just to simplify the discussion, I'm looking at the sum rule, the transverse sum rule. It's a current-current correlator, current-current operator. Since the current has both one and two body components, we can expand it. We have a pure one-body term and an interference term, which are diagrammatically shown here. So this is a pure one body, and here you have an interference where you have a one body and two body. But remember, the two nucleons are also correlated with via one pion exchange. So this is the microscopic picture of the transverse process. And these are experimental data for scattering for helium-4. This is the longitudinal response. This is the transverse, and the transverse is systematically systematically bigger than the longitudinal. Theoretically, if we were to neglect two body currents and calculate the longitudinal and the transverse, so ST and SL, they would be essentially the same. These are dashed line, represents calculation without two body currents, and leading to the same longitudinal and transverse response. If we turn on the two body currents, this mechanism leads to the enhancement that is capable of explaining the data. So the transverse response is bigger than the longitudinal. So this is an important feature of electron scattering. And the motivation to develop the short time approximation is threefold. First, we want to move from the inclusive processes and account for more exclusive processes. Second, we want to be able to include a relativistic effect in the description to push ab initio calculation to higher energy. And most importantly, we want to retain the two-nucleon dynamic that is important to explain the data. So schematically, the short-time approximation calculates the response in real time, and really the scattering is occurring only with pairs of correlating nucleons. So the active participant in the scattering process are two nucleons that are correlated, so in a sense is based on a factorization scheme. And then the probe is interacting with the one nucleon within the pair via one body current, or the whole pair via two body currents. So the interference term that I discussed is properly accounted for. Additionally, there is the appearance of this quantity, which we named response density, is an object that depends on the relative and center of mass momenta of the pair that is participating in the scattering process. And if you integrate back over the relative and the center of mass momenta, you recover the response function. But this object, in a sense, gives you more information about this pseudo final state to nucleon final state. And so you have, you can plot, this is scattering from helium-4, the momentum transfer is 500 MeV/c, this is the relative energy of the pair and the center of mass energy of the pair. This structure here that increases tail is again induced by the tensor of the two nucleon dynamics. You can also slice up this figure to select a kinematic that is convenient for experiment. So for example, in the back-to-back configuration, you can select the center of mass energy to be 66 MeV in this case, and profile the response as function of the relative energy of the pair. You can also look at the contribution from scattering from neutron-neutron pairs or proton-proton pairs. This is gives you a little bit more information than the momentum distribution, because now you have the vertex, so the electron is seeing protons and neutron as different as opposed to momentum distribution. And you also have the total response, which is in magenta, to be compared with the yellow one that is based on a one-body operator only. And the recent development have been mainly related to export this method to study carbon-12. They require a lot of technicalities in terms of refactoring the code and making it suitable to address this problem. From the densities, the responses were obtained. And finally, the cross-section. So this is a comparison with the data for cross-section at these particular kinematics. So this is the energy of the electron beam and the scattering angle. This dashed area in terms of omega and q, so energy and momentum released into the system, represents all the kinematic that we could calculate or we calculate. Whereas this solids line represents all the values of q and omega corresponding to this energy and scattering angle of the electron. So really here, in this region, we are precisely in the regime of validity of the short time, therefore the nice agreement. But if you move to other kinematics, for example, momentum transfer of 700 MeV/c, the short time as well as the green function Monte Carlo are non relativistic and are in black and yellow. They fail to reproduce the data, whereas a treatment based on the spectral function that includes fully relativistic one-body current explains the data. So essentially, this figure is telling us that we need to incorporate a relativistic effect. And this is written work done with Ronen Weiss. So the paradigm usually is to take the covariant one-body electromagnetic current operator. In order to utilize it in our non-relativistic framework, one performs a non-relativistic expansion of this operator. Traditionally, the non-relativistic expansion is done assuming that both P prime and P, so the initial nucleonic momentum and the final nucleonic momentum, are small. So that's how we incorporate the correction. But the new paradigm is that, yes, the initial momentum of the nucleon is small, but the final momentum can be large, and that can be a knocked out nucleon. So that's the development. So that, of course, led to a different expression for the one-body operator, and also a different energy-conserving delta function, because now you are in a relativistic approach. So this is all preliminary, but in order to incorporate the new one-body operator, the first step was to move from relative and center of mass energy to momenta of nucleon 1 and momenta of nucleon 2. So that's the two peaks emerging from that. And here, this figure is just a contour plot of that one, and these two lines represents the combination of P1 and P2 in a non-relativistic frame, so the red one, and with the relativistic frame in blue. And this is the figure that I showed you before where there was a disagreement. So this is the old one, and the new one is in orange with the new one-body current with proper knocked out, so to speak, kinematic at 700 MeV, which was the problem that we were having before. So this is all preliminary. This is just a teaser because yesterday Nir Barnea mentioned this paper. So these are three body densities. Ronen Weiss and Stefano Gandolfi studied them with the auxiliary field. We are currently looking at, with Graham Chambers Wall and Emanuele Beneghetti, to 3-nucleon correction in neutrinoless double beta decay potential. So, of course, the first step was to understand first the 3-nucleon density and then move on to this 3-nucleon correlation. And this is, again, another teaser, 3-body, 3-nucleon momentum distribution. So this figure is a Q. One momentum is fixed, and the other two are the same, and they are making, they are varied. And this is really a preliminary that I just throw it in there for interested people. And that's it. So I talked basically only about electromagnetic probe at various kinematic regimes, so ground state properties, shape of nuclei and nuclear response. My interest is in the role of many nucleon correlation and currents, and I'd also try to emphasize the importance of having a collaborative environment where different expertise come together to work on this problem. So this is very exciting. I would like to, of course, show and acknowledge Graham Chamber Walls, Garrett King, and Lorenzo Andreoli, who are the driving force under most of the calculation that I discussed. And here are my local collaboration, WashU, and then Garrett King, Andreoli, and Niek are Los Alamos and JLab, and also acknowledging the resources. So thank you for your attention.
So thank you very much for the nice overview. Are there questions for Saori? Yes, Daniel.
Thanks. So this is a really impressive set of results. Can you show your charge radii plot again? So it seems unfair, given all the things you got right, to ask you about something that looks like it's missing, but I'm going to do it anyway. So do you read anything into the fact that your charge radii for the trinucleons, certainly in the case of helium-3, appears it's low compared to experiment, and then that happens again in the 7-nucleon system?
Yeah, so they could be correlated because of the structure of the 7 nucleons. So they are a 3 plus a 4 plus a 3. So
then you must have thought about what might fix it, right?
yeah. But yes, so it could also be a deficiencies in the interaction and the current at the low Q.
So it's like some isoscalar part that how do you compare with the deuteron?
The deuteron for this interaction, you mean the quadruple moment at the point, or
No,
the radius?
Just the radius.
The radius is also under predict.
Okay, so there is, as you know, right,
Yeah.
an isoscalar two-body current, which is, just has to be fit eventually.
Eventually, yes.
Right, yeah, okay,
It could be, yeah.
okay, thank you.
Are there more questions? Yes? Yes. Tobias?
I enjoyed pretty much your talk. I have two questions. One is, I think, is related to this helium-3 that we see dislocated. You showed the magnetic moment.
Yes.
For Triton, look pretty good. And yes, and then you see, okay, although the error band.
This is
Yeah.
us. The pink is us.
Yeah, this is the magnetic radius. I'm meaning the magnetic moment.
Ah.
That I think is better. The data is better. Yeah, I saw that. You comment beryllium-9, but helium-3.
Oh, okay.
Yes,
So here,
yes.
this
I
this
was
calculation. So the thing that I didn't say is that in this current operator. So let me go back. Here there are these constant again that are unknown. And so basically you sacrifice some observables to fix them, and therefore these three guys, so helium-3, the deuteron and triton, are not prediction. They are used to constrain the low energy constants. Once you fix them, then all of these instead are prediction based on this constraint of the current.
Now the second question is about the second peak. Is the delta? You showed some figures that is not this one. I think was.
The second peak of.
Yeah, that is the second peak as a function of omega. You have your response function. That is the delta.
See, wait a second. You mean in the first figure,
Yeah, I think
the cross
even
section,
when you are showing
In the inelastic.
even-
the
Yeah.
responses.
Yes.
even this nucleon correlation.
Yeah.
Yes. You see
So
Yes.
yeah, so basically all of these is delta resonance pion production that is not in the theory. So our theory is really in the quasi-elastic.
Okay.
There are no real pions. All the deltas are there, but they're all virtual. So you.
I can tell why what I was wondering, if from these nucleon short-range correlations that you have these nucleons back-to-back, if you would be able to get some information about the nucleon delta short-range correlation. I was wondering if
Yeah, the
this
delta is
possible.
included by this virtual. One thing that we are working on now is to, so in this calculation, all the propagators are taken in the static limit. Also, the one pion exchange is taken in the static limit. But if you, and also the delta, but if you release the energy dependence in the denominator, you start having also those kind of announcement to get agreement with the data. So that's something that we are working on now.
So you say you have to go to a Fock space representation
Yes.
of that.
Yes.
Have the pion explicit and so on.
Yes.
Oh, a big job.
Okay, I think we can keep the more questions for the afternoon because I'm sure there are more. Let's thank Saori again.